Here we go. So we're on log expressions, and log expressions we spent an entire like 2 weeks in Algebra 2 on. And so this is not meant to be a full-on blown out section in this regards as just what the properties of logs are. So when you look up here, do these look familiar? Yes, the properties should look familiar for the most part, right? So for example, here, anything a log of 1 is going to always be 0. And the log of 0 is because you're asking the base to the 0 power, right? So remember, log, think of it as an exponent, okay? The base of the log is the base of the exponent. So when I'm reading this, it's saying log base b of 1 equals 0. I'm saying b to the 0 equals 1. Is that a true statement? Yes, because anything to the 0 power is 1. Does that make sense? Okay, so that's our first rule. Next is our, I like to call this kind of like the inverse rule. If your base and your argument are the same, that means it's going to equal 1. Identity, I guess, is what it's called, actually, identity. If the base of the log and the base are the argument are the same, it's going to be 1. Next, if the base of the log and the base of the argument are the same, then the power is the solution. Okay. Same thing here, except in reverse. If the base of your exponent and the base of your log are the same, then the argument is the solution. And these apply to natural log as well. Natural log, remember, that just means that you're using e. So natural log of 1 equals 0 means e to the 0 equals 1. Okay. Natural log and e are inverses of each other. And when you multiply an inverse times each other, they're going to equal 1. So that's our inverse situation here. And then all the other rules are the same. Natural log e is y. That ln equals log base e. So instead of writing log base e, log is what it looks like to me. Instead of writing that, that's why they created the natural log, ln. So the base of the log is the same as the base of the argument. So therefore, the power of the argument is the solution. Okay. And then the same thing here, the base of the exponent and the base of the log are the same. So the solution is the argument. All right. So these are straightforward properties of logs. And when you're doing this, remember, if there is no base, does anyone remember what that means b is? If there's no visible base, what is your b? Nobody? 10. Okay. If you see log of 5, that means that your base is 10. Log base 10. Okay. Called our common log. So when there isn't a base, then that means it is a 10, and that's our common log. This is what happens when you're pressing on your phone or on Desmos. You just type log without putting a base. That's what it's going to be in terms of 10. Got it? All right. Let's keep her going. So because of this, we're going to kind of go through, write it as an exponential, reviewing that property from Algebra 2, okay? So reviewing that property from Algebra 2, we learned that the base of the log is the base of the exponent. The solution of the log is the power of the exponent. The argument is now your solution. So what this ends up looking like, if you guys remember correctly, is that if I have log base 2 of 8 equals 3, that means that I have 2 to the third equals 8. Is that a true statement? Yes. Okay. This right here, this radical, does anyone remember what a radical means? It's square root. Why is the answer a half? Nope. Let's talk about it. When you have a square root, that means that the power of your argument is a half power. Okay. A unit power means that you are taking the root of something. A unit power means that the numerator is 1 and the denominator can be whatever it wants. But if I have a unit power, that means I'm taking the root of that number. So if it was 3 to the 1/3, I'm taking the cube root of 3, right? 3 to the 1/4, I'm taking the fourth root of 3, okay? And because of that, what happens here? The base of the log and the base of the exponent are the same, so they're going to cancel each other out, and that's why it is 1/2. Okay. I meant to rewrite this another way as well. So even if you didn't want to think about this as an exponential, you can also think about it using same base rule, because 8 can be written as 2 to the 3. The base of the log, the base of the exponent are the same, which is why your answer is 3. So if you don't want to think about it in terms of an exponent, you can always break down that number and see if the bases are the same. Okay, let's talk about fractional arguments. With a fractional argument, what that means is that it can be rewritten as an exponent of -1. Do you remember that rule from exponents? So this could be rewritten as log base 5 of 25 to the -1. That's how you take a number out of the denominator, is by putting it to a power of -1. Anything out of the denominator, you put it to a power of -1. Okay, 25, I can rewrite that. So this would equal log base 5 of 5 to the -2. Does that make sense? Do we see how we went from 25 to the -1 to 5 to the -2? Okay, and now that my base of my log and the base of my exponent are the same, it makes sense why my solution is -2. Okay, so it's all a manipulation of pieces. Does that make sense? It's a form of equivalency. This would be on non-calculator part, by the way. Okay, the use of this knowledge. Okay, now remember I talked about this. This is called common log because this is just log by itself. That means that we're supposed to know that our base is 10. And when there is no power given, what is the power? It has to be the friendly one. The base of the log and the base of the exponent are the same. So then your power is your solution. Okay, applying that same rule here, your exponent, the base of the exponent and the base of the log are the same. So what are they going to do? Cancel out. And the reason is because same base. There's really nothing else I can model it because it's going to eliminate. Don't have to manipulate it, don't have to rewrite it. It's already in the fact that I see they have the same base. The base of the exponent, the base of the log are the same. Okay. Yes. All right. So with that being said, we're going to go back to Algebra 2 again, where we talked about how to write an exponent as a log and a log as an exponent. The reason why, bless you, by the way, the reason why you're doing this is because you're just using inverse operations. The inverse of an exponential is log, right? And so if I'm trying to undo an exponent, I'm going to take the log of that exponent. Once you do it once, then you see the pattern and follow the pattern. Does that make sense? So we're going to do it the long way, and then hopefully we see the pattern. Fish. All right. So if I'm doing the inverse here, I have 4 to the third equals 64. I need to free my power. In order to free my power, I'm going to have to take a log of the same base, because isn't that what happens up here? If I take the log of the same base, then I will free my power. So I'm taking the log of base 4 to the third. The thing is, what you do to one. Okay. So what ends up happening here is that this is going to cancel out. So in terms of a log, it's going to be log base 4 of 64 equals 3. So what do you notice took place here? How did the numbers rearrange themselves? The base of the exponent becomes the log base. What else? The exponent became the solution. Argument. Perfect. There we go. So now, instead of having to do inverse every single time, the goal is that you recognize what role each value plays, right? So let's do it without taking the inverse. So starting here, what's going to be the first thing I know? Log of 9. Okay. The solution becomes the argument equals 3. The power becomes the solution. If all else fails, can you just revert back to doing inverse operations? Yes. Okay. All right. Now let's talk about when it gets a little weird. I'm like, oh, there's a lot happening here, right? I have a fraction. I have a negative power. Oh no, what do I do? Is it going to change anything? No, it's going to still all be the same process. So what is going to be the base of my log? So we have log base 2. What's going to be my argument? 1 over 32. And what's going to be my solution? Negative 5. Make sense? Okay. Don't freak out because you see a fraction or a negative exponent. A lot of times you guys are like, oh no. No, don't do that. It changes nothing. The rule applies the same. All right, here. Does it matter how large my base is? No, same process. Whatever the base of the exponent is, that is now the base of my log. Whatever the solution is, that is now my argument. And whatever my my exponent was, is now my solution. Do we see the pattern? Doable pattern? Awesome sauce. All right, because you see the pattern, undo it. Go. All right, here we go, really quick. What's my exponent? 5 what? Easy peasy, right? On B. Perfect. That means I'm asking what is the fourth root of 625? And that would be 5. That's 5 times 5 times 5 times 5 is 625. All right, C. Go. Okay. And then last but not least, got it? Remember, the negative means the solution belongs in the denominator. However, in this case, because it's already in the denominator, that means it belongs in the numerator. A negative and negative makes a positive. So we're now back in the numerator. Yes? Sure. Well, not like in that sense, like 2 bits, but yeah, because you're going to have 2 to the negative 6, which means that it's in the wrong spot. I like to think of negative exponents as unhappy numbers. I'm unhappy with where I'm at. Put me somewhere else. And you only have 2 options, either top or bottom. So if the negative's in the denominator, it's unhappy. It wants to be in the numerator. If the negative's in the numerator, it's unhappy and wants to be in the denominator. So that's how I think of negative exponents, as unhappy numbers. Make me happy. All right, here we go. So we're going to talk about common log and evaluating common log. When you're evaluating using common log, you are thinking of everything in powers of 10. Okay? Everything is in powers of 10. When you're thinking of powers and tens, remember, that's just the number of zeros at the end. Does that make sense? Yes? So 10 to the 1 is what? 10, because it's 1 with how many zeros? 1. 10 to the 2? 100. Oh my God. 10 to the 3? 1,000. 10 to the 4? Oh my gosh. Y'all are so good. Look at y'all doing that mental math. Okay? That's how powers of 10 work, right? You have 1, and the power just tells you how many zeros to add on to it. That is what our place value system is built on. Yes? Should have learned that in elementary. Yeah, I know. It's crazy. That is literally what your place value system is built on, is the powers of 10. Okay? Yeah, no. The 1's place is 10 to the 0. 10's place, 10 to the 1. Yeah, that's crazy. All that stuff you learn sometimes. All right, so what is the solution here? What is the log base of log of 100? 10 to what power? 2. Boom. Does that make sense? And how do I know it's 2? There's 2 zeros. That's it. Y'all see that? You see her? Yeah. You just write 2. That's the answer. Okay. All right. This one's a little trickier, but it's really not. Okay. Remember, when there isn't a log base, the base is automatically what? 10. So if I have 10 with the argument of 10 to the 1/2, what is my answer? 1/2. Because the log base and the exponent base are the same. So they're going to do what? Cancel each other out. Okay. Remember, a radical is just a unit fraction power. A radical is just a unit fraction power. Your unit fractions are 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. You should have learned that in elementary school. Don't know why you did it, but that's what a unit fraction is. Okay. All right. Next. What about this one? How many zeros are there? Where are they? So it's going to be what? -3.
We're just changing the sign from positive to negative because
It's in the denominator. It's a fraction. So 10 to the -3rd is 1/100,000, which is where your decimals come from on the right side of your place value. 1/10, 1/100, 1/1000. Yeah. These are things, again, from elementary. Just want to put that out. So don't blame me if you didn't learn that. So you know. All right, what about here? The 6's become what? A 1. So then I'm just left with what? 10. Because first part here is you deal with your exponent, right? And dealing with my exponent, what happens here? They cancel out. They come cast with a friendly 1. And 10 to the 1 is just what? 10. Okay? You are expected to know these little patterns to be able to do on the non-calculator part. Okay? All right. All right. Let's talk about ones that you would have to use with a calculator. If it appears with a decimal, that means it's on the calculator part of the test and you are expected to use a calculator. With the calculator, you are expected to round to the nearest 3 decimal places as your output. Does that make sense? Okay. So this is just simply, can you type in a calculator and round correctly? That's essentially all you're doing. Okay. This would be on an FRQ, so it would be part of a process, not the final solution. Does that make sense? Yes? Okay. So just really quick, in the calculator, I'm assuming 9 times out of 10, most of y'all are going to use what? Boo. Just so lame. Okay. When you're on Desmos, you're literally just going to type log. L-O-G. And then put in 34, what was it? 34.5. And that's it. Okay. If you're using Sylvie, she'll round for you. But if you use this, it does not. So please make sure you round correctly. So what does this round to? 1.538, 1 in 538, correct? Agreed? I'm not going to do any more calculator problems with you because that just sounds pointless. So I'm not going to do them. But really? Really? You can't type in the calculator? You can't type log? Okay. We're going to pretend that you didn't say that. All right. But can we understand? Now, what I do want to talk to you about is a negative argument. Okay. You guys remember what the log function looks like? The log function is the inverse of an exponential function. Exponential functions have horizontal asymptotes. Do you remember that guy? This is exponential. Log functions have vertical asymptotes. So I have a limit on my x. And what can my x not be for a log? Negative, because there is this vertical asymptote. So if my argument is negative, that means that no real solution. It does not exist. I don't have to even use a calculator because if I remember the properties of my log, the log function cannot have negative arguments. Does that make sense? Okay. And that's because it's the inverse of an exponential. Exponentials have horizontal asymptotes. Logs have vertical asymptotes. So it affects my x and not my y. Make sense? Okay. Now, if this was a log transformed instead of a straightforward log, then of course it'd be different. But it's a straightforward log, right? I don't have plus or minus or multiply, anything on top of that. All right, questions about part A of this? Easy peasy. Okay, do we feel like it was more of a review? Because it should have felt more like a review than completely brand new. Yeah? All right. So we're going to go on to the next part, part B. Oh, the picture, or in words, summarize the picture. Yep. So remembering that there is a vertical asymptote. So whatever tip you need to remind yourself why x has to be greater than 0. Okay, so next part is evaluating logs. Okay. So evaluating logs, again, there's gonna be, if it's a non-traditional looking, it's gonna be using a calculator. So these are examples of where you would have to use a calculator in order to evaluate the log. Because besides the first one. The second one's a pretty good too. Yeah. Well, example 6 is non-calculator. And then example 7 is calculator. Example 6 problems, you should be able to tell me 2 to what power. Remember, logs is asking you 2 to what power makes this. Does that make sense? So 2 to what power makes 32. So when you're thinking about evaluating a calculator, a log without a calculator, you're asking yourself 2 to what power equals 32. You're asking yourself here 49 to what power equals 7. You're asking yourself here 164 to what power equals 4. You're asking yourself here 5 to what power equals negative 25. Okay? That's how you should think of when you're evaluating a log. Make sense? Okay, so on the first one, somebody, 2 to what power is 32? 5. So our solution would be, I'm just going to write x equals 5. Right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. Yes? All right. Scale 49 to what power equals 7? Notice that I am getting smaller, right? If I'm getting smaller, that means that I have to have a fractional power. Why is it 1/2? The square root of 49 is 7. Okay? So this would be x equals 1/2. That's because the only way 49 can become 7 is by taking the square root. And 1/2 means, a power of 1/2 means I'm taking the square root of 49. With me? Okay. Next, we have a fraction here. We have 1/64. Okay. 1/64 means that I have 64 to the negative 1x equals 4. I know that it has to be negative because it is a fractional base. Does that make sense? So I know it has to be negative. And again, I'm going from a big exponential base to a small solution. So I know it has to be what? A fraction, right? So 4 times itself, how many times will give me 64? 4 times 4 is 16. 16 times 4 is 64, guys. 16 times. Oh, didn't hear you. Well, what? Not negative 3. Negative 1/3. So it has to be negative 1/3 because my base is larger than my output, right? Yes? Or in the case of the log, my base is smaller than my argument. Is what makes it negative and what makes this have to be a fraction. Okay? All right, here, 5 to what power equals negative 25? Is that possible? What did we just talk about? The arguments of logs, guys. They can't be what? Negative. There's no way 5 to anything is going to equal negative 25. Is it? No, and then looking back at my argument, it's less than 0. So therefore, there is no solution. That came out real weird up there. Let's try that again. There she goes. No solution. NA, undefined. No. All right. The next part is just practicing putting in the calculator. So because you're using Desmos, I do want to go over with you, just making sure that we all are comfortable changing the base in Desmos. So when you're inputting a different base in Desmos, you're going to type LOG and you're going to hit Shift Dash, which is the button next to 0. So you hit Shift Dash and now you can input whatever base you need. Does that make sense? So what base do I need for the first problem? 3. Log base 3, and you're going to arrow over and then parenthesis put in what you need. Okay. In order to do it, you have to hit Shift Dash. Now, if you are a person who is not a hater on Sylvie, huh? Okay, y'all are haters. So alpha window, and you just go to log base, and you just type it in, and she'll round for you. So I'm just saying, all of Sylvie's haters lately. I feel like it was the worst thing that we ever did was allow Desmos in an AP course. It takes away the yes, it does. All right, so when you type it in, so I have 3. I typed 3 already. And I'm gonna put 15. And you know what? I don't want to have to think too bad. So I'm gonna go over here and round. And Sylvie's gonna do the work for me. Your precious Desmos would never and could never. So just saying. Just, no one asked. Okay. Once I do it once, I don't have to do it again. Okay. And it's just there. But that's it. I'm not gonna go through every problem on 7 with you. I'll leave it for you to complete your own. But again, in Desmos, what do you have to press in order to change the base? Shift 6. I said shift dash. Okay. Shift 6. I don't know where that came from. Who said shift? That's the power. And I was like, why do we say that? Where'd my pen go? Go back. All right. So if I was you and I need to remind myself, I would write here Desmos. I'm going to press shift. No, that is not allowed to be said again in 2026. It is banned in my house. It is banned in my house. It is not, we are not saying it. Every time my kids say it, they lose time, screen time. That's where we're at. They lose minutes off their screen time. Yes, I'm serious. I don't want to hear that again. Like, I'm supposed to be at home and be okay, but I have a 5-year-old and a 10-year-old. So I'm trying to write dash. That says dash. We're going to go with it. But again, you cannot ask anyone, how do I do it? Remember, Desmos, you have to press what? Shift and dash. All right. So where does all this come into play? As we're going through this unit, we're going to be applying our log rules by solving real world problems and applications. That's where it comes in. So like this was all fun and dandy, learning the rules and practicing it. This is where the implementation comes. Okay. So here really quick before we start that, I just want to make sure that we are okay with the patterns that you see and that we can do this just fine. Okay. So with the calculator, really quick, I would like for you to practice or without a calculator, because I feel like you honestly can do this without a calculator. But I'm going to give you 2 minutes to find the pattern of what you see between these numbers. Because that's all log is recognizing a pattern. That's all math is. Patterns, patterns, patterns. Have y'all found it? Was it terrible? No. I believe in you. All right. Are we ready to talk about her? Okay. What happened in the beginning? What do we have 1.4. And then what happened? Oh my God. And then what happened? And then it would keep going, right? Just for the sake of it, I'm going to show you. And so if I need to figure out 10 to the 10, what did that come out to be? Oh my gosh, look at that. So what? Oh, that's a weird 7. Trust it, it's a 7. So what do we notice? What's happening here? What's the pattern with the integers? It's just your natural numbers, right? 1, 2, 3, dot, 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 10. It's the, like you said, it's just your what? Exponents. It's the exponents of the 10. What is the pattern of the decimals? Pattern is they are the same. They all are the same, and that is just 0.477 whatever. All right, so let's talk about orders of magnitude. When you're talking about orders of magnitude, what you're doing is you're comparing the powers and finding their difference. So when it says, what is the order of magnitude greater is 3 to 10, then 3, 1, you're looking at their powers. So this is 10, this is 1. You're literally subtracting. 10 minus 1 equals 9. That's your order of magnitude. How do you feel? All right. Where that comes from, I will complete these notes so that you'll have them. But what that comes from is comes into Richter scales. So this is leading us into our first real example where we'll be using the power. Make sense? All right. Your assignment is in the basket on your way out if you want to grab her. I just laid it down in there. I told you it was coming.
Hey, we looked for that.
So why are y'all acting surprised? All right, so here we go. We're going to be talking about the intensity levels of 2 earthquakes measured on a seismograph. And the formula that we would be using is log of I base 1 divided by I base 2 equals M sub 1 minus M sub 2, okay? Where M is the magnitude given by the Richter scale. Okay, so it says, how many times more severe was a 2001 earthquake in Bihar, India? All right, so I got cut off. So the Richter scale here. So we have log of I1 divided by I2 equals M1 minus M2. Okay, so it says how many times more was a 2001 earthquake in Bihar, India than M1? M1 equals 7.9, and then in 1999 earthquake in Athens, where your magnitude of base 2 is 5 and 9/10. Okay, so all we're simply doing here is subtracting for the most part. So you have your M1 minus your M2. So your M1 is 7.9. So we have 7.9 minus M2, which is 5.9. And it equals log base of your intensity. So log of intensity 1 divided by intensity 2. Okay. And so what we end up here, 7.9 minus 5.9 is 2. So 2 equal, oh, that got weird. All right, so back to what we're doing. So here, grab the pen. So we get 2 equals, and now we're left with log base. This isn't y'all, sorry. So now we're left with log of intensity 1 divided by intensity 2, and it is equal to, okay? Essentially here, our job is to get to the intensity by itself. So to find the intensity, we're going to use our inverse operations. Our log base here, it's common log, so therefore it's a base of 10. And so in order to get rid of this, we're going to raise everything to the 10 on both sides. This is going to cancel out using our log properties. So we're left with 10 to the 2 equals our intensity of 1 divided by intensity 2. So therefore, this equals 100. So the earthquake I don't know why I can't write. It's like I go on the break and I can't remember right. The earthquake in India is 100 times greater than the Greek earthquake. I did not leave myself enough room right. That says earthquake by an order of magnitude of 2. Whatever the power is on the 10, that's your order of magnitude. So the order of magnitude here is equals 10. Not 10, 2. And that's that. Okay. Another example of using log and properties without a calculator. Okay, here we have our pH scale model. So your pH scale equals negative log of H hydrogen plus, right? A scale that measures how acidic or basic a substance ranks. The scale ranges from 0 to 14, where 7 represents neutral, and each full pH value below 7 is 10 times more acidic than the next higher value. Okay, so starting off, we have so to start off here, we're gonna have our hydrogen ion concentration. So hydrogen ion concentration, we're gonna look at vinegar. So we're looking at vinegar, and the vinegar is at 2.4. So we know that its pH is 2.4. So 2.4 equals the negative log hydrogen, positive hydrogen. Okay, that 2.4, if I'm trying to find this, again, we're going to use inverse operations, which means I'm raising it to the base of 10. All right, so now when we are taking this base, notice that it's a negative log, and that negative actually means that this is going to be 10 to the negative 24 equals, and it's going to be H plus. Sorry. Hydrogen plus. And when we put that in the calculator, we end up getting that it's 3.98 times 10 to the negative 3. And I'm not a chemist, but I'm pretty sure the units are molecular liters. I think so. Okay. So then I want you to pause. And so we did vinegar and follow the same process. I want you to pause and do the same thing with the baking soda. Okay. All right, let's see how you did on baking soda. So for baking soda, we're just going to call it soda. So for baking soda, our pH is 8.4. So therefore, we're going to start off with 8.4 equals negative log. Okay, and we're going to do the same thing again. We are using our inverse operations. Notice here that it's negative. We're going to divide by a negative, which means now we're going to make the 8.4. I didn't really tell you why this became negative on this side. I apologize, but we're dividing by a negative so that we can start off. So the first thing is to get the log by itself, which means that I had to remove that negative. And so now we're going to raise it to 10, raise it to 10. Inverse property cancels that out. And we're left with 10 to the negative 8.4 equals our height. Okay. Type that in the calculator and we get 3.98 times 10 to the negative 9 molecular. I hope I'm saying that right. All right. Okay. So now we're going to say how many times greater is the hydrogen ion concentration of vinegar than the baking soda? Okay. What we're doing is we're dividing to find that greater. So we're dividing vinegar divided by baking soda. And what we end up here was we're comparing this is the same. So it doesn't really matter it's 3.9, but what we're comparing are their exponents. So we have, well, not this part. I don't know why I did that. This is the same. We're comparing the exponents here, the 10. What are our powers? So we have 10 for vinegar. We were at 10 to the negative 2.4. And for baking soda, we were at 10 negative 8.4, which gives us negative 2.4 minus 8.4, right? When you're dividing and the bases are the same, that means you are subtracting the power. So negative 2.4 minus negative 8.4. A negative times a negative makes a positive. So this leaves us with 10 to the 6. This leaves us with 10 to the 6. Okay. What does that 6 tell us? Well, that 6 tells us that vinegar is 6 orders of magnitude greater than baking soda. Baking soda. All right, and that is it for this.